Good evening everyone. So welcome to my online class. So today we will discuss about the magnetostatics. Magnetostatics deals with magnetic field produced by steady current. As you know that the static charges produce electric field and the moving charges produce magnetic field. That one is the basic of magnetism. That means the magnetic field. So today we will discuss about the magnetostatics. That means the magnetic field produced by steady current. So first of all, you see there is a resemblance between Coulomb's law for electrostatics and Biot-Savart's law in magnetostatics. Similarly, in electrostatics there is Gauss law. Similarly, the resemblance of that one in magnetostatics is Ampere's law. So today we will discuss the magnetostatics. In magnetostatic portion we will discuss Biot-Savart law. So first of all, as we have discussed, the magnetostatics deals with magnetic field produced by steady current. So first of all, for Biot-Savart law, what is Biot-Savart law? That's what we will discuss. Biot-Savart. Now this Biot-Savart law is used or is applied to determine the magnetic field intensity or the magnetic field strength at a point. That means suppose with reference to this figure, the point is P and IDX is the current element and the distance between the current element and the point P where the magnetic field strength is to be determined is R. So it states that DH is equal to, or it is proportional to, you can say it is equal to the strength of, that means it is proportional to ideal and inversely proportional to, now we are taking this scalar form, and inversely proportional to the square between the distance between the current element and the point P. So mathematically, if we will expand this one, dH is equal to some constant and that is 1 by 4 pi into ideal divided by R square. Now this one is the scalar form. If we are going for the vector form, this will be dH is equal to 1 by 4 pi into 1 by 4 pi into, so this one is the constant, ideal cross AR divided by R square. That is, this one is the vector form. So if we want to find out the magnetic field strength, we have to take the integration. So integrating this one, we'll get H is equal to 1 by 4 pi, as it is constant, it can be taken out. So ideal cross, in place of R, AR, that is the unit vector in the R direction, we can write R vector by R magnitude. So this one will be RQ. How the direction of the electric field intensity is being found out? It is proportional, it is perpendicular to the plane containing IDX and R. That means the current element and the R, distance between the current element and the point P. And the direction will be given by corkscrew rule. Suppose we are moving corkscrew rule. That means if you are finding out the direction, if you are moving the IDX current element in this direction, in the direction of theta, it will be inward the paper or into the paper. That's how the direction of the magnetic field intensity is being found out. So H is equal to this one. Now we can write this one is, so H is equal to 1 by 4 pi integration ideal cross R divided by R magnitude, R vector magnitude Q. Now we know that the magnetic flux density and the magnetic field strength are related by the equation B is equal to mu into H. So from this we can write B is equal to mu by 4 pi ideal cross R divided by R vector magnitude Q. Now you see, you take the divergence in both the sides. So if we take the divergence, it is a constant. So mu by 4 pi, it will be divergence of ideal cross R, and 1 by 4 pi 1 by R cube, it is the magnitude. It can be taken from the divergence, out from the divergence. Now you see, this one is the equation. Divergence of B is equal to mu by 4 pi integration 1 by R vector magnitude Q divergence of ideal cross R. Now we know that from the basic of vector calculus, divergence of U cross B is equal to V curl U minus U curl V. U curl V. So all these are vectors. So I am giving the interpretations. Now applying those basics, we can write divergence of B is equal to mu by 4 pi, and this one will be 1 by R vector magnitude Q. So we can write D curl U, that means R curl ideal minus ideal curl R. Now we know that the curl deals with the rate of rotation. Now you see, if you are taking the current element Idx, there is no movement of the current element. So that means the curl is 0 here. Similarly, if you are taking the position, that means the distance vector, that means from the current element to the point P where the magnetic field strength is to be found out, there is no rotation of this vector. So that means both are 0. So we can say from this to divergence of B is equal to 0. That means what it signifies exactly, that is very important. So this equation represents that the magnetic field is solenoidal field. That means whatever flux is entering, that much flux is leaving the surface. So that means it signifies that unlike electrostatics, where the electric flux lines emanate from positive charge and terminates at negative charge, there is no such source and sink in case of magnetic field. That means whatever flux is entering the surface, that much flux is leaving the surface. That means that's why isolated pole does not exist. That means the magnetic field is solenoidal field. So thank you all for watching. So please like, share and subscribe to my channel. Thank you all.